let's get started. I'm going to give Matt the full hour for him to talk to us about his work. All right, now you're excited. It's Friday. Come on, let's get started. All right, thank you. All right, so welcome to the last colloquium of the semester. It's my pleasure to introduce Dr. Matthew Kohn, who's joined us today from Boise State University. Rumor has it he's in town to help with the defense. Anybody in the audience worry about that?
I'm sorry, what?
He's here for the help with the defense. I mean, it's Kaylee's defense, right? She's looking nervous. But we've also invited him here to give us a colloquium. So Matt is a geochemist who studies geochronology and metamorphic materials. He's done this since his PhD. He's also interested in stable isotopes and believe it or not has paleontology under his belt. So for the people who are interested in that, you should definitely chat with him a little bit after the seminar. Today he's going to be talking to us about shear heating, controls on mineralogy, and seismicity and convection and subduction zones. So let's give him a very warm welcome.
Thanks. Well, it's a real pleasure to be able to come out here and talk to you about one of my favorite topics, metamorphic petrology. I do have to say, it's especially gratifying to come to a department that has geophysicists who think about things that are deeper than about 100 meters, because that's the group at Boise State. They're a very fine scientific program there. It's a little hard for me to talk to them about things like subduction zones and what the mantle wedge looks like. But today I want to talk about thermal structure in subduction zones in the context of metamorphic conditions that are derived from rocks that are exhumed from subduction systems. There is a cast of characters. Adrian Castro is a graduate student with Frank Spear. Frank Spear was my PhD advisor, so there's a direct link there. And then Cesar Renero is also helping me to understand more about geophysics. Okay. So I think we all know why subduction zones are important. Of course, they are a source of a number of hazards, including volcanoes like this one, or tsunamis like that one. I will point out that there is an initiative to develop a better understanding of subduction zones, the SC4D initiative, which one of your own, Sarah Penniston-Dorland, has contributed to. And of course, subduction zones are more generally of interest to geologists because there are lots of interesting things that go on here besides earthquakes and volcanoes related to the subduction of lithosphere to create this volcanic arc and produce continental crust and so on. One of the great advantages of looking at subduction zone metamorphism is that you get to look at some really attractive rocks. So here, for example, is, maybe it doesn't look attractive to you, but it does to me, a lawsonite blue schist here in thin section. It looks like this with these beautiful blue amphiboles. And then eclogites, the hallmark of high pressure metamorphism, with some nice clinopyroxenes, and these are garnets over here. Now, within the context of thermal evolution, there is a class of models published by Syracuse et al. In 2010, which looks like this. So these are a series of models that are developed for all of the active subduction zones on Earth. They all have different input parameters: subduction rate, age of the subducting plate, the thickness of sediment, and so on and so on. So what you're looking at is a series of a bunch of different subduction zones. That dark purple line is the mean of all of those subduction zones. What you find essentially is that the colder ones correspond with old crust and the youngest ones correspond with extremely young crust. So for example, if you look at Cascadia, it's less than 10 million years old. The younger plate is hotter, you get a hotter thermal model. That's why these data extend over into that region. I will be showing this average geotherm through a lot of the slides here. And I neglected to point out this is pressure on the vertical axis versus temperature on the horizontal axis. These are the dark gray lines are the different metamorphic facies. You don't have to worry about the ones that are down here, but there's the blue schist facies here, the eclogite facies there. Those are the hallmark of subduction zone metamorphism. And there's also this boundary which metamorphic petrologists refer to either the forbidden zone or not realized on planet Earth. And the reason for that is that as of the time that I'm giving the talk today, there are no metamorphic rocks that we know of that have been exhumed from that region. Okay? And of course, what you see is that many of the thermal models actually enter into the forbidden region. The average here skirts the forbidden region. And so that leads you to speculate, is there some bias that occurs to metamorphic rocks, or is there some misparameterization of the models? So for example, you might not exhume rocks that are from the coldest subduction zones, so we don't pick them up, so we don't see them in the rock record. That's what thermal models look like. Of course, there are many different thermal models, but these that I'm showing you, the Syracuse et al. Models, probably have the highest citation rate of anything that's been published in the last 10 years. This is the paradigm of subduction zone thermal structure. Now, if you look at a paper that Sarah led a couple of years ago, this simply illustrates the point. All of these little dots in here are different pressure temperature conditions that have been derived from rocks exhumed from subduction zones. And what you see is, there are a couple that come close to the forbidden zone, but they don't actually enter into it. And one of the things you notice, of course, is that the dark blue, I think is supposed to be the color, that this line that runs through the mean or median, doesn't really matter, of the data points is considerably hotter than the average subduction zone thermal model. But it's not just that it's hotter, it has a different curvature to it. Okay, so you can play around with various parameters in a thermal model. It's very hard to change something like the curvature to it. So when you look at the thermal models, they're curved in this direction. When you look at the rock data, they're curved in that direction. And just to illustrate the point, if you look at pressures corresponding to depths of about 50 kilometers, so that's in this region right here, then you find the greatest disparity in the pressure. So this would be the apparent temperature normalized to a thermal model, and you find that the rocks are, on average, 300 degrees C hotter than the Syracuse et al. Models, and then it's a couple hundred degrees C relative to another class of models led by Taras Guria. This matters, okay? It really matters whether you get the correct temperature or something else in a subduction zone. And yes, it's actually important to geophysicists, not just to petrologists like me. And one of the things that I'm going to talk about is the seismic-aseismic transition, which occurs and so this is a whole series of seismic events imaged along a subducting slab. This is a schematic from Hooray et al., 2011. And what you find is that for a given subduction zone, there is a distribution of earthquakes with depth such that there's a peak in occurrence, but then there's a point where it dies out. And that's called the seismic-aseismic transition. There are lots of different ways to define it. If you define it differently, you will shift that boundary up or down. But what's interesting about it is that it's a fairly consistent depth across all subduction zones. So if you pick one particular criterion to define it, then it is at approximately 50 kilometers depth. And you find this for many different sorts of slabs. So if you're looking at the Japan or Kermadec or the Eastern Aleutians, which are all different subduction zones, you find that the subduction, the seismic-aseismic transition occurs within that range. Now, that depth is important for us because that's where you see the maximum disparity between the temperatures that we infer from metamorphic rocks and the temperatures that are predicted by subduction zone thermal models. So if you're going to look at an area where it makes the biggest difference, that's the place to look at it. So it's important to geophysicists. It's important for lots of other reasons. I'm going to touch on this particular topic. But of course, it matters to petrologists too. So a lot of times we think about the evolution of metamorphic rocks along the subduction interface. The interface is simply where the subducting slab interfaces with the overriding slab. There's a region in here. And in fact, the metamorphic rocks that are exhumed from subduction zones they pretty much come from this interface. You can show this based on various structures that are in those rocks. And so why this matters, well, there are lots of reasons. There's fluid release, there's mixing that goes on. This is where a lot of geochemical cycling occurs. It's also has importance for what kinds of reactions that you see, what different mineral stability fields there are. And I'm not going to go through these diagrams in any great detail. They are incredibly complex when you look at all the different mineral assemblages. But again, if you look at a pressure versus temperature diagram, so this is the region of the seismic-aseismic transition. These are essentially important mineral reactions in different bulk compositions. So if we're looking at a metamorphosed mudstone, then you form form fluids at various reactions. Chlorite goes to garnet, chloritoid goes to kyanite, glaucophane goes to clinopyroxene. You don't even need to know what these minerals are particularly, except that these all have water in them, these are all anhydrous. And as a consequence, where these reactions occur, depends on what the temperature is. So if you've got a cold subduction zone, you're not crossing a bunch of these reactions. If you have a hot subduction zone, then you are crossing them. So this is one where lawsonite disappears, garnet forms, and kyanite forms. What that means is that in different subduction zones, if you have different temperatures, those reactions and the fluid productions will occur at different depths. Different bulk compositions, you see basically the same thing. There are reactions that remove hydrous phases. There are reactions that bring in anhydrous phases. So that would be for a metabasalt. And then if you're looking at an ultramafic rock, there are similar kinds of reactions. Brucite is a strongly hydrous phase, serpentine, talc. So these are reactions that are removing minerals that have very high water contents to produce minerals that have lower contents. Now, when Sarah and I and Craig Manning published this paper back in 2015, we identified some sources of heat that might explain this disparity of what we see between the modeled subduction zone thermal structure and what we see in metamorphic rocks. Okay? So yes, there could be bias to what's being exhumed from a subduction interface, but we thought maybe there are these other sources of heat that might come into it. And we identified 5 of these. Shear heating we thought would be the greatest contributor. This is effectively the contribution to surface heat flow. That's what these components are. So this is 20 milliwatts per meter squared. In the continents, the average is 40 to 50 milliwatts per meter squared. The other sorts of things that come into play are radioactive decay, is a little bit rock convection, where you're advecting heat up through the system, which shows up in some models, but not others. Mineral reactions, if you hydrate a bunch of anhydrous rocks, you generate heat. Let's see, I did radioactive decay, so fluid advection is another way to change the heat budget. And so you can see these are ranked in terms of importance. Well, it turns out I'm the one who made these calculations. And so this is sort of an average distributed contribution of shearing to the heat budget. And it turns out it can actually be considerably higher. This is a more accurate characterization of what is possible in a subduction system, so that these other contributors are down here. You can get a lot of heat out of shear heating. It depends on the circumstances, depends on what the coefficient of friction is, but in principle, you can increase the amount of heat that's coming in, and this can contribute significantly to the thermal structure. That is the point of what I'm going to present here, that basically if you introduce some shear heating, then you can effectively reconcile the thermal models with the rock record. Okay, so if you don't remember anything else, please remember that one point. Okay, so how do you quantify shear heating? You go back to basically heat conduction. So this is simply Fourier's first law of heat conduction. It says the heat flux, for example, milliwatts per meter squared, that's a heat flux, is proportional to a thermal conductivity and a temperature gradient. And if you're like me and you're a geochemist, you might be more familiar with this equation, Fick's first law, which says that the flux of a chemical species through a particular area is proportional to the diffusion coefficient and the concentration gradient. exactly the same mathematics. There's a famous book published by Cronk, 1975, basically the mathematics of diffusion. I'm pretty sure every equation that was published in that book was equivalent to the thermal equivalent published in Carr's Law and Jaeger like 20 years prior to that. In fact, if you go and you look at Carr's Law and Jaeger, there's a lot more examples. They're actually a lot more interesting in some ways. So it's quite interesting that the geochemists in this case have borrowed the mathematics from the geophysicists. Maybe it's not surprising to the geophysicists, but okay, so what you can then do is you can take Fourier's law and you can integrate it so that you get temperature not in terms of a differential, but temperature in terms of stuff that you care about and can measure. And effectively, if you take this equation and you simplify it, or you what do you do? You expand it to systems that are relevant to a subduction zone. What you find is that the temperature in a particular point is proportional to the basal heat flux. That's the heat flux that's coming into the base of a slab. There's a heat production term, which is over here. This is the thermal conductivity. This is a distance scale. But what's important is that as long as you cast your equations in terms of shear heating, you will introduce this other term. So this is the sigma is the shear stress along a planar surface, and V is the velocity along which that shearing is occurring, which is perfect for what you want to describe in a subduction zone, right? Because you have a plane interface, or you have a subduction interface, which to all intents and purposes is a planar interface. There's a velocity by which the subducting slab is transferring material along that interface. And if there's a coefficient of friction, that is, if there's a shear stress along it, you will create heat. Okay, so what does this mean? That means that Q naught, which is the basal heat flux, establishes a temperature gradient. So this is sort of the simplest temperature gradient that one might consider. But that temperature gradient is then modified by a component of shear heating and a component of radioactive heating. We don't really have to deal with radioactive heating. It's a small component. But I'm simply putting this up here to explain that you're effectively taking a simple system and you're adding different components of heat. Most of us are familiar with radioactive heating. What this does is it introduces another term which is proportional to, which is effectively shear heating. Okay, so what is this controversy? Well, what modelers have argued, or some modelers have argued, is that there's very low heat flow in the forearc. And because there's such low heat flow, you really can't have shear heating. So if you have shear heating, you produce a higher temperature along that interface, that heat has to go somewhere. And if it goes out vertically, you're in the forearc of the system. If you don't see anomalous heat flow measurements in the forearc, you don't have shear heating at depth. A corollary of this is that exhumed blue schists and eclogites are completely anomalous. So, right, that was the point that I was making before, that if the models are correct, then the rocks that we get out of subduction zones must somehow be anomalous. Maybe they're reflecting the exhumation of rocks from subduction zones with anomalously young crust. There are some issues with that with respect to petrology that I'm not going to go into right now. But if there is this bias to what's removed from a subduction zone, then it may not tell us anything directly about the thermal structure, or it could be biased in some way. And then the question for me becomes, well, is this really true? Is shear heating really zero? Does the forearc heat flow really imply there's no shear heating? Or does it say maybe there could be shear heating, but it would be a small component? If there is shear heating, does it make any difference? Maybe it's a trivial component, we don't have to deal with it. And the way that I have dealt with this, which is essentially how all the theoretical derivations of this is in terms of an apparent coefficient of friction. So this is the shear stress, this is the apparent coefficient of friction, and then the shear stress is a function of the apparent coefficient of friction times depth. Okay, well, it turns out there was a paper published a few years back that looked at not the whole suite of subduction zones that occur across the Earth, but about a half a dozen of them. And this paper by Gao and Wang in 2014 shows the 4-arc heat flow data and then what it takes to model those heat flow data in terms of a shear heating component. Okay? So if you see an apparent coefficient of friction that's 0, it means you don't need shear heating to explain the heat flow data. If you see anything above that, then the idea is that shear heating is creating the anomalous heat flow that you see at the surface. Okay, so this is the Japan trench, which is, not surprisingly, in Japan. And so these are the heat flow data. And these are different models to try to explain the heat flow data. The best fit model for this is with a heat flow, with a coefficient of friction that's 0.025. Okay, that's 2.5% of the total stress, vertical stress that's exerted on the interface. So it's a small component. And I don't know, you could look at this and say, well, a shear stress component, an apparent coefficient of friction of 0, doesn't do a bad job of explaining the data. It's true that 0.025 is a little bit better, but that coefficient of friction is pretty darn low. Okay, that's one subduction zone. Here's another one, Kermadec, out in Tonga. This is a paper published by von Hertzen et al. in 2001. They cast it in a rather different way. These coefficients here are cast in terms of the pressure increase with respect to kilometers. But basically, what you find is that these curves that are in here, a value of about 0.5 on this scale fits the heat flow data better. 0.5 corresponds to an apparent coefficient of friction that's now about 6%. Okay, so that's a bit higher. And you can see that an apparent coefficient of friction of 0 fits exactly one data point out of the entire data set. So it's pretty obvious that this has to have some coefficient of friction to explain these heat flow data, assuming that the elevation in heat flow is the result of shear heating. And then if you look at Hikurangi, which is in New Zealand, they did not even plot a coefficient of friction equal to 0. What they found is that this black line that goes through the data is the best fit to the heat flow data. Now the apparent coefficient of friction is about 13%. And there are various compilations. There's actually one back from the sort of early 90s that effectively came to exactly the same conclusion. If you want to explain the 4-arc heat flow, then you need to include a shear stress component. And so these are the numbers we're talking about, as low as 2 to 2.5%, up to, well, let's just call it between 2 and 10%, okay, or 2.5 to 10%. It is true that the heat flow data are not super sensitive to shear heating, but it is nonetheless true that there is no best estimate, which are these dots through here, that is equal to 0. I mean, there is, it would appear that there is always a shear component to the heat flow that you observe in 4 arcs. And this is just, well, Wen Lu could comment on this a lot more knowledgeably than I, but when I look at some of the rock mechanics literature that talks about the coefficient of friction in various materials, values that are on the order of 0.1 are pretty easy to get to. You take the weakest sheet silicate likely to occur in these systems, which is talc, and you get an apparent coefficient of friction that's about 0.1. When you start talking about serpentine and other phases, that's way up here. So in fact, the problem is not finding a coefficient of friction in a single mineral along a thin plane that can explain the coefficients of friction here. You're actually left with trying to explain why it's as low as what you see here. That there must be some other mechanisms for reducing the apparent shear stress, or the apparent coefficient of friction. So I actually compiled a bunch of data. Well, I didn't do this. Carol Stein did this in 2003. She was very kind to send me all of the heat flow data that went into this compilation. This is heat flow that is normalized to the heat flow, the basal heat flux into the subducting plate. Okay, now you need to do that because if you have a young plate, it's going to be hotter. If you have an old plate, it's going to be colder. So what you do is you normalize the heat flow to the heat flux in the plate of that age. So that would be the heat flux corresponding to the plate of that age. And then you normalize the distance, right? Because all of these plates are subducting at different angles. The arc is going to be at different distances. Your forearc is going to have different distances. So this is normalized to the distance to the arc. So this is at the trench. This is at the arc. This is somewhere out in the ocean before you get to the subduction zone. And what you find is that, well, it's not too surprising. Heat flow is moderate in the subducting slab, okay, before it begins subducting. I know these numbers are not equivalent to 1, which they should be. I think that's because I'm taking a mean there, and you get these funny anomalies that go into it. If you take a median, though, you're pretty much spot on to what you would anticipate from the heat flow into a plate of that age. And what you find is that this comes down and then it flattens out. But it's never zero. It's never zero. So when you look at plates worldwide and you look at the heat flow and you normalize it so you can compare them all together, you know, you really can't explain these data with a coefficient of friction that's equal to 0. Okay, so we know it's not equal to 0. The question is, does it matter? And it turns out there's an analytical solution to this, and it's basically for a dipping shear zone. These guys were interested not necessarily in subduction zones, they were interested in the main central thrust in the Himalaya. But the results are equally applicable to a subduction zone. And it basically says that this is the same equation that I was showing you before, except without the radioactive heating because it's so trivial. So you have the basal heat flux, you have the shear stress here, and there's a term here which is S, and S is in terms of all of these different components. And basically what this says is that if I am subducting a slab that has a velocity v at a particular angle, depends on the angle, this is the thermal diffusivity over here, and of course it depends on depth, that this factor, well, this factor is always greater than 1, okay? And so this expression of temperature as a function of depth is always going to be less than the temperature that you would infer if it were not being subducted, okay? So if it's just a flat shear zone. And what this means is that, not surprisingly, if you go to a subduction zone and you put all of these terms in, put in the shear heating, but also account for the movement, the advection of cold material down the subduction system, then the temperature is going to be lower. Okay? That's pretty much all it says. And it will be lower by this particular factor. Now, there is another extension of this, Titcheler and Ruff, 1993. Those are the guys who did the calculations of the coefficient of friction in different forearcs. So this was, 20 years before Gao and Wang published their results. But they basically came up with the same idea of the same results of a coefficient of friction not equal to 0. Titcheler and Ruff also developed this same concept, but they had a more complex geometry, which is more representative of subduction zones worldwide. They're not planes, they're curved. Okay, so we can go back to this equation, and it's really this S parameter that becomes important. You can describe it in terms of a Peclet number, which is looking at the ratio of advection to heat conduction. So you're basically adjusting the temperature according to, you can think of it as the Peclet number. And so whereas this would be the solution to the heat flow equation without subduction, this is the solution to the heat flow equation with subduction, where that S parameter comes in. And so basically what you're looking at is the slab top geotherm and everything above it. But if you're looking at the temperature structure along the slab surface, the slab top geotherm, it's essentially a standard geotherm like this, corrected for, well, with shear heating, corrected for the subduction, the advection of heat. Okay, so I did some models on this. I used the Molnar and England model. I used, this is sort of the reference here. Well, this is the reference. The geometry is based on, there's a compilation of subduction geometries. It's called Slab 1.0. I think they're now Slab 2.0. That it's either just coming out or came out recently. Turns out if you go to central Chile, then the geometry of that subduction zone is more or less in the middle of subduction zones worldwide. And so I took this geometry as characteristic of the average subduction zone. The average convergence rate in subduction zones is about 6 centimeters per year. Average age of subducting plates is about 50 million years old. That defines the basal heat flux, because basal heat flux depends on the age of the crust. The reference is a minimum coefficient of friction, 2.5%. That's at the bottom of that range of coefficients of friction. And I also thought about the effects of thermal weakening. I should point out Simon Peacock did all of this 20 years ago, but I reproduced all his calculations to make sure I understood what they were all about. But I also made direct comparisons to the petrologic data that we've collected or summarized. So this is the sensitivity to the coefficient of friction. And what you find is that the thermal models are incredibly sensitive to the coefficient of friction. So if you look at a reference model, so this would be coefficient of friction, which is 0. The Syracuse et al. Models have a coefficient of friction that is equal to 0. And you increase that coefficient of friction to 2.5%, then it increases temperature by, I can't really see the scale, easily 100 degrees C in the range, at the depths that we are interested in looking at. And one of the things you'll see is that this low value of mu actually skirts the edge of the data from Penniston-Dorland et al. 2015. So this is the 95% limit of all of those PT data. Even the smallest coefficient of friction that's been inferred from heat flow data will explain one edge of that. And then as you go to higher and higher coefficients of friction, it's pretty easy to get pretty high temperatures. So the implication is that in Hikurangi, with a coefficient of friction is 10%, you're looking at temperatures that are sitting out here. They may not even be in the eclogite facies. They may be in one of these other facies like the amphibolite facies. Age doesn't really matter a whole lot. There is sufficient heat that's produced by shear heating that the age of the crust doesn't make a whole lot of difference. Turns out the convergence rate doesn't make a lot of difference either. And the reason for that is that you've got two balancing components. If you have the plate going faster, you are advecting colder rocks faster. So you create a colder subduction zone. But the amount of shear heating that you get is proportional to the velocity. So if you increase the velocity, then you increase the temperature. So the velocity increases, you're advecting a colder conditions, but you're creating more shear heating. And so these tend to balance out, so you don't really see a big effect of subduction rate. The angle of subduction actually makes a pretty big difference too, although I haven't tried to deal with that in any kind of systematic way. But this is our reference model, and all I did was take the angle and make some factor of it, increase it by a factor of 1.5 for here, divide it by a factor of 3, and you can see that this makes a difference. Another important component, though, it turns out, is thermal weakening. Thermal weakening. And so what happens is, if you look at the shear stress that rocks are capable of withstanding as a function of temperature, then you find that, well, let's see, maybe I can see this. At 200 degrees C, you can withstand a shear stress that is enormous. Okay, it's a couple of kilobars. But that as you decrease temperature to 400 degrees C, this stuff is like putty, right? It shears really easily. And there are different thermal weakening temperatures depending on what material you're looking at. Granites with a bunch of quartz in them are pretty weak. Basalts with a bunch of chain silicates are a lot stronger. You look at a peridotite with a bunch of olivine and pyroxene in it, it's stronger still. But what you see is that there's a whole range of temperatures that are possible. Okay, they're not really granites in subduction zones, or they're a small component, but metamorphosed sediments are comparable in terms of their overall bulk composition. And we do have basalts, and we do have ultramafic rocks. But nonetheless, you can think, well, what would be the effects of thermal weakening on different sorts of materials? And I wasn't going to deal with a peridotite because it's so strong, and there will always be weaker minerals. But I did look at the effects of things that vary in composition from quartz weakening in a granite versus the weakening of a metabasalt. What thermal weakening does is it creates curvature to the predicted slab top geotherm. And so each of these geotherms that's coming out here, it's easiest to see this on the red curve. So this is a coefficient of friction that's equal to 0.1, okay? And then there are different temperatures of thermal weakening. So each of these curves has 3 different temperatures of thermal weakening. And so this is the lowest temperature of thermal weakening, intermediate, highest temperature of thermal weakening. So all these 3 red curves are mu is 10%. The blue curves are 5%. You don't see them on the 2.5% because they're so cold. You just can't see them. They all pile up on the, 2 of them pile up on the one that doesn't even have any thermal weakening. And what that does, like I said, is it creates curvature. And that's probably important for understanding the petrologic data because, if you didn't have thermal weakening, these things would go out in this direction, but adding thermal weakening causes them to curve upwards. And so, in fact, if you look at a whole range of models that correspond with what is actually a fairly conservative range of the parameters that you might put into normal subduction systems, what you find is it's not very hard to reproduce the Penniston-Dorland et al. Model. And in fact, I would argue that it would be very hard to produce a thermal model that did not in some way cut through the Penniston-Dorland et al. Data set using just normal subduction parameters that you see in modern subduction zones. Okay, so these are analytical models, okay? They are vast simplifications of what really goes on in subduction zones. And fortunately, it turns out there are a set of numerical models. So very similar to the parameterization of the Syracuse et al. Models from 2010 that are so cold. But these are parameterized with coefficients of friction designed to reproduce what you see in 4-arc heat flow. Okay, so this is the most internally consistent comparison between what has been accepted in the Syracuse et al. Models by a large group of researchers over the years versus what you would get if you include shear heating. And I'm going to show you the sort of the 2-dimensional results of these models. And they're, it's really complicated, but I will ask you to look at just the 400 degree C isotherm, where that occurs in each of these models. Yeah.
Before you move on, I want to quickly ask a question about
Sure.
the dependence upon the geometry of the slab.
Mm-hmm.
It seemed like there is a strong dependency on that when you run these models, but how much is that able to bring like the 0 shear heating model over to the right so that it becomes feasible? Like, is it unrealistic geometries for the slab, or is it?
You could shift these around a lot. Yeah. You would expand this one if you used the oldest slab, the lowest coefficient of friction, a velocity that would give you a cold conditions, the lowest temperature of thermal weakening, and you increase the dip on the slab, you will pull this over to essentially the forbidden zone. You won't pull it into the forbidden zone, but you can get pretty close. And if you change it, if you say it's a really shallow slab, then you're sitting over here in the amphibolite facies, below blue schist and eclogites. Yeah. So that's why I say this is a fairly conservative range of possibilities. It's just that even with the fairly conservative range, you can reproduce the Penniston-Dorland et al. PD15. That's how several of us refer to it. Okay, so what I want you to look at is the 400 degree C isotherm and the depth at which that occurs. Okay, so here's one model. This is Japan. And you find that this is at 62 kilometers. So that's the trench. Okay, the arc, I don't know where the arc is, somewhere back over here somewhere. And so you see this characteristic, you're advecting heat, so the isotherms get bent down. But at any rate, what you calculate is a temperature of 400 degrees at 62 kilometers. This is Sumatra. Yeah, so now the trench is over here. It's subducting the other direction because Sumatra's in a different part of the world. Yeah, anyway. Depth is now at 40 kilometers. And then you go to Manila, somewhat younger subducting slab, higher coefficient of friction here, and you get a depth that's 30 kilometers. Okay, so you can move the temperature around a lot depending on the coefficients of friction. This one is the highest. I neglected to point this out. Let me back up a second. This is a fairly low coefficient of friction. And then this is now a high coefficient of friction. So varying coefficient of friction, various other parameters. You can shift the thermal structure up and down that subduction interface. Now what's interesting is when you plot these slab top geotherms, now I'm just showing you three of them, Honshu, Sumatra, and Manila. So this is Japan Trench, this is in Indonesia, Philippines. You get hotter geotherms, right? These are things that fall within, more or less, would fall within the PD15 data set. What's interesting about these particular subduction zones is that these subduction zones were also modeled in Syracuse et al. So you can make a direct comparison between a model that includes shear heating and a model that does not include shear heating. And these are the results of those. So I've color-coded these. The blue curve here for Honshu corresponds with this one. Green curve for Sumatra. I'm not able to pick it out. Oh, I guess it goes through here. Yeah, okay, so it runs up through here. That's this curve with shear heating. The red curve is for Manila, and I'm reading these off of the figures because I haven't gotten the actual data, numerical results yet. But it's sitting up here somewhere. And what you find is that these temperature increases are enormous. Okay, so the lowest coefficient of friction, 0.025, increases temperature by 125 degrees. When you look at high coefficients of friction, like Manila, you're looking at temperature increases that are on the order of 300 degrees C. So it's basically, what is it, 50 degrees C per percent increase in the coefficient of friction. So shear heating, it's important. And so then the question becomes, how do these models compare with rocks? I didn't put the PD15 envelope up there for you to see, but that's the envelope. That blue field is the envelope, and what you find is that, again, not very hard to reproduce the PD15 envelope of PT conditions. That is, these are normal subduction zones. These are subduction zones that we see around the Earth today. And in fact, they span the pressure temperature conditions that are recorded by rocks, which means the rocks are not anomalous. They're the kinds of rocks that you would expect to come out of modern subduction zones. And again, that thermal structure is important because it controls lots of different things: mineral assemblages, fluid release, heat flow, and so on. And now, let's see, with just a few minutes remaining, I'd like to talk a little bit about seismicity. Go back to this question of the seismic-aseismic transition. This turns out to be a real problem. It turns out to be a real problem because if these are the different thermal models, these black lines that run through here, so you can imagine in a colder subduction zone, the seismic-aseismic transition occurs at a greater depth. Because why? The temperature defines thermal weakening. The temperature defines the mineral reactions that you see. The temperature defines how fluids are being released. It's very hard to come up with a consistent depth to the seismic-aseismic transition. So this is, if you just pick any one of these gray bars, which is the temperature of thermal weakening, you cannot produce weakening, which might control seismicity, within the range of the seismic-aseismic transition as defined by seismic data. So you can't do it with a single temperature of thermal weakening. You can't do it with a reaction either. So this is one specific reaction. Okay, the reaction might produce fluid that catalyzes the fracturing of rocks because of a high pore fluid pressure. And when you trace that reaction up through pressure temperature space, you get, this thing is like way off the top, you get a range of pressures that does not correspond with the seismic-aseismic transition. And you know what? It really doesn't depend on what rock type you look at. So this is for an ultramafic rock. What you find is that, if you track one reaction, lower pressures to higher pressures. If you track another reaction, sure, you can reproduce the seismic-aseismic transition within the middle of the seismic-aseismic transition, but you get a bunch of data that are way off the top. So, you cannot do this. The same thing is actually true of the Syracuse et al. Models. If you go back and you track out, in this case, different reactions or temperatures of thermal weakening, you get a range of predicted pressures, if for temperature of thermal weakening or a reaction that comes through here, that does not correspond with the seismic-aseismic transition. This is not specific to thermochemical modeling of assemblages. This is just straight up looking at the Syracuse et al. Models. So then the question becomes, how do you explain this? And the short answer is, I don't know, and that's why I'm happy to talk to people here. You cannot do this with thermodynamics. You cannot do this with mineral reactions. So my thought is, what if this seismic-aseismic transition really doesn't have a lot to do with temperature per se? So it's not related to mineral reactions. It's not related to thermal weakening. Maybe it has something to do with the presence or absence of the weakest rocks that are along that subduction interface. Now, the weakest rocks are going to have the greatest buoyancy, as it turns out. And so if you're looking at a system like this, so you've got the oceanic crust and the lithosphere underneath it. This is the overriding crust, the mantle underneath it. And you've got some carapace of sedimentary rocks or chemically mixed rocks, things that might have talc in them or micas or something that's particularly weak. There might be some mechanism, and I'm not positive what that is, that these materials basically pinch out with depth. So you actually lose them from the subduction interface. You might have little vestiges that occur down here, but they do not form an interconnected sheet that is then capable of defining the strength of that surface. And in fact, what that'll do is that will couple, in a viscous sense, the oceanic crust with the mantle over here. That would actually drive mantle convection if you can remove these slippery rocks. And so in principle, this might explain the decoupled seismically, or mechanically decoupled, this is the seismically coupled region, through a process by which they go through this transition of essentially having weak material up here, having strong material down here, that there is some process to remove the slippery material in that region. There are various data that could be explained by a process like this, so that you have some anomalies that could be interpreted as temperature. That's commonly how they're interpreted. But they're also dependent on what kind of rocks you see. So in principle, it may not be true in this case, but in principle, you could have material down here that just does not have weak rocks along it, and that you do have rocks that are up here that are weak and have slow seismic speeds. And that transition is, about 60, 75 kilometers. It's more or less in the region that we're talking about. That process, hang on, let me go back for a second here. So this process, if you're really scraping off material down here, it's got to go somewhere, right? And so this gives you a mechanism for taking material down. If it hits some blockage down there, so it doesn't penetrate any further, it's got to come back out again. And so that may be the reason that we see a bunch of different rocks. We see melange zones with rocks of different bulk compositions. So you've got an eclogite over here and an amphibolite here, lawsonite blue schist. That's where the lawsonite blue schist is. Do not go there. One of our collaborators went there and regretted it for the next 2 weeks. There are green schists over here, more eclogites, and so on. There's a range of different metamorphic conditions that can reflect this backflow of material. And there's an interesting thing that we've discovered when you take all of these pressure temperature conditions and you plot them as a cumulative probability plot. So this is probability, no pressures to, you've looked at all of them. There's actually a kink at about 80 kilometers. So there's something fundamental that's changing in subduction systems with respect to what's getting exhumed from the subduction as metamorphic rocks at a depth of about 80 kilometers. So to finish up, heat flow implies shear heating. I don't think you can get away from that, or at least there's got to be some source of heat to produce that. It is not, everything is, temperatures are all low in a subduction zone, right? But they're not that low in the forearc. There is some other component of heat that comes into it. The thermal effects of shear heating are large. Even the lowest coefficients of friction that people have inferred from forearc heat flow will increase temperatures by 100 or 200 degrees. And so, if you put in different models that have reasonable parameters as we understand modern subduction zones today, it's not very hard to reproduce the pressure temperature data. This is the tough thing. How do you explain the quasi-constant depth of the seismic-aseismic transition? Can't do it with thermal weakening. You can't do it with mineral reactions. My argument is that there is some kind of strengthening of the slab interface, that you're removing the weakest materials, you are viscously coupling the downgoing slab to the overriding mantle. And this occurs at a depth of something like 50 kilometers, maybe a little bit deeper, depending on how one thinks about how this stuff all evolves. And then I'm still trying to think about this. Why is there this kink at 80 kilometers where you get a lot more subduction zone metamorphic rocks exhumed from shallower levels than from deeper levels? Okay, I'd like to thank the folks who fund me, mostly the Tectonics program over the years, but also the international program. And then, of course, Sarah Penniston-Dorland here in our audience, Peter Molnar, who held my hand through the trials of thermal modeling using his analytical solution. And then also Kellen Wang has provided some input into the numerical models. And I'd like to thank you for your attention.
So your shear heating here.
Oh yeah.
So your shear heating, do you need to worry about the thickness of the deformation interface?
Right, that's a great question, and it's one I've been asked before. As long as the shear interface is thin with respect to the thickness of the the column of rock that you're talking about, then it doesn't make any difference. It could be, and actually I don't know enough rock mechanics to know this, it could be that as you increase the thickness of the shear zone, you will decrease what we calculate for the apparent coefficient of friction. Right, so that's another way of taking the rock mechanics literature that would say the coefficient of friction is pretty high if you, that's across a planar interface, right? If you increase the thickness of that interface, I think, but I'm not positive because I don't know the rock mechanics well enough, but I think that will lower the apparent coefficient of friction, and that could be one reason why the apparent coefficient of friction that you need to explain the forearc heat flow is lower than you would get from those simple experiments. But yeah, the fact is, we kind of have a sense of the thickness of the subduction interface from looking at metamorphic rocks where these materials are exposed on the surface, and they're not that thick, right? So they're a small component of the total rock column. Yeah.
So staying on that very low coefficient of friction, all the calculations you had there did not consider any fluids or any heat that might be transported by a fluid. So could it be that you actually have more heat being generated with a higher coefficient of friction, but it doesn't stay there? It's been advected by fluids.
Yeah, there's sort of a competing effect. So we know that this was a question that we just talked about earlier today, that we know that there are fluids that are being expelled along the toe of the wedge. So if you look at heat flow, and you look right at the very edge of the decoupling as it breaches the surface under the ocean. But where it comes up to the rock surface, there is anomalously high heat flow there. And it's because there's fluids that are being expelled along that. But that has a twofold effect. One is that you're moving heat from lower down to higher up, but you're also cooling rocks at the surface. And what that does is there's a paper that, I'm forgetting the first author's name, but Kellen Wang is on this, that it shows that you actually cool off everything. So the initial subducting slab is actually colder than you would predict from these simple models. So, I mean, in some sense, yeah, you can move temperatures up, but it has a corresponding thermal effect on what's being moved downward. And I don't know how those balance out, but it is something I would be delighted to talk with you or anybody else who has a perspective on that.
Okay, as a rock mechanics person who
Yes.
sits here, I'm getting totally confused about the later part when you discuss the seismic to aseismic transition. What is the confusion about the thermal weakening and the chemical reaction controlled behavior? What are you looking into?
Yeah, so the thing about thermal, this is one of the explanations for how you go from a seismically active region to something that produces no earthquakes. One of the arguments is that if the temperatures are high enough, the rocks are so ductile that they basically cannot fracture. They're just too weak. So if you pick a temperature and you look at all of the different thermal models that have been predicted for the active subduction zones on Earth, you say, look, here's my temperature, and you look at where that falls with respect to different thermal models that have been predicted for these same subduction zones, you don't get a consistent depth. Okay, so it's very hard to see how a thermal weakening argument actually works. All the subduction zones, they've got a sedimentary carapace that's going down. Those rocks should be getting weaker and weaker and weaker as you go with depth. And yet when you look at a cold subduction zone where they are going to be the strongest, and a weak subduction zone where their strength is disappearing at really shallow depths, you nonetheless see a consistent seismic-aseismic transition. It's really hard to see how a thermal weakening will create such a consistent location of the seismic-aseismic transition.
That's because it's not a thermal weakening. We know
Exactly.
that, right?
Yeah, right. It's not thermal weakening. But the same argument applies to reaction. So people have suggested that what drives seismicity is the production of fluids, the decrease in increase in pore fluid pressure, the decrease in the effective pressure. And, but you can't do that with these rocks either, because the reactions are, we talked about this morning, the reactions are almost vertical in pressure temperature space. So it's kind of like the same argument for thermal weakening, that if you look at a cold subduction zone, where you cross a particular reaction is going to be at much higher pressure, much greater depths than crossing that same reaction in a warmer subduction zone. So again, you don't get the consistency of the seismic-aseismic transition. So the only way I can explain this is, well, those rocks aren't there anymore. Somehow they've been removed. But the mechanism by which that occurs, boy, that's a tough one for me. There's a question in the back.
Oh yeah. In these subduction zones, does the importance of shear heating, does it vary in space and time in the same subduction zone? Like maybe the angle changes or the velocity changes, and then is there some kind of scale where you can quantify spatially what that variability is, or how it might change over time in that same subduction?
That's a great question. So I think what you're saying, for example, is if you look at a single subduction zone and you look at, say, the northern part and the southern part, do you see different coefficients of friction that would give rise to different heat flow, so that you would see different magnitudes of heat flow along that? Despite the fact that the subducting plate age is essentially identical, the sedimentary carapace is identical, and so on. I don't know of any data that look like that. There are some data, well, there are distributed data for the Japan Trench, but there aren't sufficient data along a single transect that you would be able to convince yourself of that. If you look at the Tonga Kermadec, there are two transects, north and south, And those show essentially the same heat flow. So you don't see it there. And I don't know another data set that has the correct distribution of measurements to see that. So the only one I know of is Tonga Kermadec, and it does not show that. Yeah.
How are they collecting the heat flow data?
I'm sorry.
How are they collecting the heat flow data?
Yeah, so there are two ways that they do this. The conventional way, it's been around for a long time. It's like the coolest thing. I love how this works. But you take a big probe, and I think it's 2 meters long, so basically as long as we are, and you drop this thing down into the sediment. And this is the cool part. They're effectively thermometers along this thing. The act of shoving this thing into the sediment creates a thermal pulse, right? So it's just a frictional increase in temperature. And the rate at which that pulse decreases as you go outward from the probe gives you the thermal conductivity of the material that you just stuck the probe into. So that's part of the thing that you need to determine the heat flux is the thermal conductivity. And then after everything is equilibrated, you get a temperature gradient. Okay, so the heat flux is proportional to the temperature gradient and the thermal conductivity. You get the thermal conductivity from the transient temperature changes, and you get the thermal gradient from the equilibrium temperature gradient. Those two together go into making the heat flux, or the heat flow measurement. So that's the first thing, and then the second thing that people do is there are bottom simulating reflectors. So if you use seismic data, you can see the sediment water interface. There are other reflectors that are parallel to that interface. Those reflect the present, those indicate the presence of clathrates, which are materials that have a particular thermal stability. So if you know the temperature at the depth of the bottom simulating reflector, which we think we know from thermodynamics, and you know the depth of the sediment water interface and the temperature there, you can get a temperature gradient. And if you assume a thermal conductivity, you can get the heat flow from that.
Do you allow another question?
Of course.
Okay, this will be a potentially quick one. That's if shear heating with the subduction is so important, what can you say something about for when I was a graduate student, the biggest thing is they missing shear heating in San Andreas. Numerous heat flow measurements, numerous earthquakes, right? And rock types and everything. We couldn't find the shear heating. So now with the new, in light of the subduction rocks, what do you now say about what we're missing in the San Andreas?
I don't think you're missing anything. A lot of it depends on the confining pressure, right?
So it only happens at 40, 50 kilometers and below.
Well, that's where the maximum component, the maximum contribution of shear heating is, right? And that's the part that I care about because that's the biggest disparity between the thermal models and the data, right? The rock data. But yeah, I mean, if you go down and you look at what's happening closer to the surface, all those models converge because shear heating in shallow levels isn't particularly efficient. And then it also depends on the coefficient of friction, right? So if you look at the San Andreas Fault, as I understand it from the couple of papers that I've looked at, there is talc along that fault. So it's about the weakest material you can think of.
Rule out talc in any of those interface, right?
I'm sorry, say that
I
again?
think it would be hard to rule out any of the talc or stapelites and these kind of clay minerals in any of those subduction interface.
No, not in those subductions. I'm thinking about the San Andreas Fault, though. As I understand it, there is talc along that.
Yes,
along that
it's
shear zone.
minute amounts from the cutting, and I wouldn't be surprised to see minute amount of talc in any of those subduction
Right.
rocks.
Well, in subduction zones, that's where the fluid flux becomes important because, so I had a master's student who was looking at ultramafic blocks within the Franciscan, effectively mud matrix, and you do find talc developed along them. It's because you're adding silica through fluids to the ultramafic rocks. So, this whole concept that Hindman and Peacock published in, or maybe it's Peacock and Hindman, whichever, in 1999 that, it may be talc that's controlling the strength of a subduction interface. That makes petrologic sense. It's certainly feasible. Will?
So one more question. Go ahead.
So you're talking about losing a lot of the subduction interface to explain the seismic-aseismic transition. Do you see that reflected in the rock record in terms of the textures, outcrop scale textures of exhumed rocks? Do you see less block and matrix in rocks that are exhumed from below whatever the 50-kilometer mark?
I don't know. That's a good question. The rocks that are the deepest, that are greater than 80 kilometers depth, those are almost all, if not all of them, from continent-continent collisions. Okay, so in the explanation for how you even get those rocks is it's effectively a plunger process. You stuff this big, thick slab of continental crust, and it squirts out these materials, but they're squirted out as thrust sheets. Okay, they are not isolated blocks. There may be one or two exceptions, but that's that's how those things come out. In terms of the other deep versus shallower sections, I mean, there are a lot of these are in thrust sheets. They're not necessarily from melanges, but whether there is any systematic distribution with respect to depth, that I don't know. That's a good question.
Okay, well, let's say that one more time.